Hello and welcome back to another daily math video. And today we're asked a question from American High School Math Examination from the year 1981. And the question states if theta is a constant such that theta is between 0 and pi, and the equation x plus 1 over x is equal to 2 cosine of theta, for each positive integer n, find x to the nth power plus 1 over x to the nth power. It has to be in terms of n and theta. Interesting. So this problem seems to be centered around this equation right over here. So from this equation, we're supposed to figure out what this expression is equal to. And it has to be in terms of n and theta. Well, an interesting method of tackling this problem would just be to solve for x in this equation and plug in for this equation, and we might get an expression that simplifies very well in terms of n and theta. So let's do that. To solve for x in this equation, we multiply through by x, and bringing this term to the other side, we get x squared minus 2x cosine of theta plus 1, because 1 over x times x is 1, is equal to 0. So these two equations are equivalent. Using the quadratic formula with a is equal to 1, b is equal to negative 2 cosine of theta, and c is equal to 1, because those are our coefficients. Then we get x is just equal to 2 cosine of theta, which is negative minus 2 cosine of theta, plus or minus the square root of b squared, which is 4 cosine squared of theta, minus 4ac over 2a, and a is just 1. So simplifying this, we can take a 2 out of the square root, factoring out a 4, and then that becomes a 2 once you take it out of the square root, where you get 2 cosine of theta plus or minus 2 square roots of cosine squared of theta minus 1. And let's recall an important trig identity here. Cosine squared of theta minus 1. This is just the same thing as negative 1 minus cosine squared of theta. And remember, 1 minus cosine squared of theta is just sine squared of theta. So cosine squared of theta minus 1 is just negative sine squared of theta. So that means square root, this inside here is just square root of negative sine squared of theta. So canceling out the 2's for both the numerator and denominator, we have x is just cosine of theta plus or minus square root of sine squared, or negative sine squared of theta. And remember, whenever we have a negative inside a square root, we can just take it out and it becomes an I, which is square root of negative 1. And it's the imaginary unit. And also, square root of sine squared of theta is just sine of theta. So we get x is equal to cosine of theta plus or minus I sine of theta. And this actually simplified quite well, especially considering that our radical simplified really easily, and it canceled the 2 really nicely, and we can use a nice trig identity to simplify it really well. All right, so remember, it's asking us for positive integers, n. So that means we can apply Euler's formula. And Euler's formula, in case you don't know or you aren't familiar with this, there's tons of materials online which will give you a lot of information, but Euler's formula relates the exponential function and trigonometric functions. So, for example, what it says is e to the I theta is equal to cosine of theta plus I sine of theta. And that's very interesting because this is very similar to cosine of theta plus I sine of theta, just plus or minus. So one more time, e to the I theta is cosine of theta plus I sine of theta. So e to the I theta, when we raise it to the nth power, because we want to plug x in over here, and it's raised to the nth power. So we need to raise this expression to the nth power. So whenever we raise a complex number to the nth power, because e to the I theta is cosine of theta plus I sine of theta, when we raise e to the I theta to the nth power, it's just the same thing as e to the I n theta. And n theta becomes our new angle. And e to the I n theta is just cosine of n theta plus I sine of n theta. Why? Because the argument inside the sine and cosine is always the coefficient of the I and the exponential over here, and the exponent. That's interesting. So that means cosine of theta plus I sine of theta to the nth power is just cosine of n theta plus I sine of n theta. Interesting. And this very important identity follows from the exponential rule, the exponent rule, where we can multiply powers because these two expressions are equivalent. And just to clarify things, I wrote it down here. So e to the I theta to the nth power, just cosine of theta plus I sine of theta to the nth power. And these two expressions are the same. And this expression is the same as cosine of n theta plus I sine of n theta. So therefore, these two expressions are the same. And this is kind of a miracle almost. Because it's interesting how, let's say, because it's n's a positive integer, remember? So that means you can expand this out by multiplying this n times by itself. And that means if we multiply cosine of theta plus I sine of theta by itself n times, it's just the same thing as just multiplying the angle inside by n for both the cosine and the sine function. It's very interesting. And that just follows from this rule of multiplying exponents over here. But it's very, very interesting. It's something I would not overlook. If you're interested, please read more materials online. I'm sure they have a lot of videos up there. And they'll provide much more insight than I'll delve into in this video. So now that we have that down, remember, we have plus or minus I sine of theta. Cosine of theta plus or minus I sine of theta. So this can also be negative. So you need to take care of the negative case as well when you plug into x to the n plus 1 over x to the n. So to do that, we'll look at a similar expression. This time, we'll similarly use Euler's formula, except we'll do e to the I negative theta is just equal to cosine of negative theta plus I sine of negative theta. And because sine is odd and cosine is even, we have this simplifies to cosine of theta minus, because whenever you plug in a negative argument into an odd function, you can just multiply it by -1 and put in the positive argument. So it's cosine of theta minus I sine of theta. And that's very interesting. We can similarly apply in a similar way we did before, raising to the nth power, e to the I negative theta to the nth power is just cosine of theta minus I sine of theta to the nth power. And these is just equal to this, because the rule of exponents, multiplication, allows us to multiply. So this is the same thing as e to the I negative n theta, which is just, this is just the same thing as this by Euler's formula again, because negative n theta or n theta is a new angle. So this is just equal to cosine of n theta minus I sine of n theta. So because these two expressions are equal, and by exponent multiplication rule, these two expressions are equal, and these two expressions are equal, we have these two expressions being equal. Interesting. So this takes care of our negative case, where there's a negative sign in front of I sine of theta. And now that we have this, we can just proceed to plugging in to our expression over here for x. So plugging in, x is equal to cosine of theta plus or minus I sine of theta into there. This is just the same thing as cosine of theta plus or minus I sine of theta to the nth power plus 1 over cosine of theta plus or minus I sine of theta to the nth power. And using the rules we derived earlier, namely cosine of theta minus I sine of theta to the nth power is cosine of n theta minus I sine of n theta. And the previous very similar one we derived here with the plus sign instead, we can simplify this to be just cosine of n theta plus or minus I sine of n theta. And this denominator simplifies to cosine of n theta plus or minus I sine of n theta. And we're almost there to finding our expression. Now we just need to rationalize the denominator here. And it will simplify a lot. So to rationalize it, remember we multiply by the complex conjugate. So we switch the sign between a and b, where the number in the denominator is a plus bi. So we multiply by cosine of n theta minus plus I sine of n theta. So we switch the signs. we can do the exact same thing with the plus or minus as with just the plus or minus. It's just you're just taking care of two cases at once, and very interesting. So multiplying by the conjugate, and the denominator, if you expand it, we get cosine squared of n theta plus sine squared of n theta. And in the numerator, we just have this expression, because 1 times this expression is just cosine of n theta minus plus I sine of n theta. Remember the Pythagorean identity? This simplifies to 1 because n theta is in both the cosine squared and the sine squared. These two have to be the same inside the cosine and sine function. And our fraction just simplifies to cosine of n theta minus plus I sine of n theta. And plugging this in for our fraction here and simplifying this expression, we have x to the nth power plus 1 over x to the nth power is cosine of n theta, and then plus or minus I sine of n theta plus cosine of n theta minus plus I sine of n theta. We're just adding these two expressions over here. And miraculously, or not that miraculously, but these two terms cancel because plus and minus plus are opposite terms. And in the end, combining like terms here, we just get x to the nth power plus 1 over x to the nth power is just 2 cosine of n theta. Finally, that's a very, very interesting method to tackle this. Today is very interesting that we could just rationalize this denominator and we could take care of two cases at once, both the plus and the minus case. Very interesting. And we used a bunch of trig identities, like here, the Pythagorean identity, here, identity in disguise. It's very similar to 1 minus cosine squared of theta. And we just had to apply a bunch of skills that we learn everywhere in math. It's not necessarily very difficult, it's just the way you need to apply them sequentially can get confusing. But still, very interesting problem. I'm not sure if these later problems, this is a later problem from AHSME 1981. I'm not sure whether they'd be this easy nowadays, but it's certainly not very easy, especially for 1981. I hope you enjoyed the video, and if you liked it, please like the video and share your comments if you have anything to share down below. Also, if you want anything or want me to solve a specific problem that I have not attempted on this channel yet, please by all means comment down below and I'll look and I'll try to create a video about that. Thanks. Bye-bye.